66 million years ago, the Earth was teeming with life. Paleontological records from the late Cretaceous period show that dinosaurs occupied nearly every major ecological niche on the planet, with no evidence of biological stress or decline. But a massive piece of rock was heading directly toward them. An asteroid roughly 14 kilometers across was moving through the vacuum of space at a velocity of 12 kilometers per second. Its trajectory put it on a direct collision course with the Yucatan Peninsula in Mexico. Specifically, it was aimed at a shallow sea covering an area known as Chicxulub. The specific chemistry of this impact zone is what sealed the fate of the dinosaurs. The shallow waters here sat on top of deep beds of carbonate and sulfate-rich rock. Hitting this exact geological target turned a devastating local collision into a global biological collapse. When the asteroid made initial contact with the Earth's crust, the kinetic energy instantly vaporized rock and blasted immense volumes of water and sediment high into the atmosphere. This simulation shows the crater's first 10 minutes. Ejected debris initially formed a wave 4.5 kilometers high. At 5 minutes, falling ejecta slammed back down, violently distorting the seafloor. By 10 minutes, this stabilized into a massive 1.5 kilometer tall rim wave. To put that energy into perspective, this tsunami was 30,000 times more powerful than the 2004 Indian Ocean tsunami. The water moved with such velocity that it scoured the ocean floor thousands of miles away, completely wiping out entire marine sediment records. While devastating, this mega tsunami was only the regional opening act of the disaster. The physical shockwave was about to be followed by a much slower atmospheric collapse. We know exactly when this happened because of this distinct horizontal sediment layer, the KPG boundary, shown here with a quarter for scale. This thin band of rock is found all over the globe and is packed with iridium, an element rare on Earth but extremely common in asteroids. Remember those sulfate-rich rocks beneath the impact site? When the asteroid hit, the heat instantly vaporized massive deposits of gypsum. This injected millions of tons of sulfuric acid aerosols straight into the stratosphere. Combined with soot from continent-spanning wildfires and pulverized rock dust, this created a thick, planet-wide haze. Sunlight reaching the surface dropped by over 50%, plunging global temperatures down by as much as 7 degrees Celsius for decades. Without sunlight, photosynthesis stopped. Plants on land and phytoplankton in the oceans quickly died off, severing the foundational link of the global food chain. Large herbivores starved first, quickly followed by the massive carnivores that hunted them. The animals that managed to stay alive were detritivores, creatures capable of feeding on dead organic matter, worms, and insects. In this freezing, pitch-black environment, survival turned on a specific trait: the ability to find calories when the sun no longer reached the ground. The non-avian dinosaurs lacked this trait. Because they were warm-blooded, they required massive amounts of food to sustain their fast metabolisms. And since they lacked the anatomical ability to burrow deep underground or dive into deep water, they had no shelter from the sudden extreme cold. Meanwhile, their close relatives, early birds with beaks, had a distinct advantage. While tooth-bearing reptiles struggled to find fresh prey, beaked birds with powerful gizzards could crack open hard seeds and nuts buried in the soil, giving them a vital source of calories. Small mammals possessed a similar edge. Their size allowed them to retreat into burrows, sheltering them from the initial intense heat pulse and the prolonged freeze that followed. Once the dust settled and the skies cleared, the Earth was empty of its apex predators. This ecological vacuum triggered rapid evolutionary divergence. Surviving mammals expanded outward, evolving new forms and sizes to fill the vast niches left completely unguarded by the dinosaurs. Without that exact sequence of events, mammals might have remained small, subterranean creatures indefinitely. The eventual rise of primates, and ultimately humans, traces directly back to the specific geography of that impact site, 66 million.